Today we're going to start talking about the other properties of water, and we're going to talk about my favorite property of water, density. So guys, I studied chemistry. I went to a university that specialized in environmental chemistry. So I learned a lot about this stuff, but I never really thought about, or I never did a course on, say, fish or aquaculture. And one of the properties of water, the property of density, is actually amazing at how it protects marine or, just quite simply fish in the water. I never really thought about it. How, where I'm from, there might be trout or small fish in the water. How do they survive the winter? Like, don't they freeze? Wouldn't they die if you froze the fish? How does this happen? And it's related to density. So the property of density is actually quite amazing. It really is an important property, and definitely, I know you can't see my face, wink, wink, a property you need to know. You definitely want to know about density. For anybody who wants to know what I look like, by the way, you can check out that lab video. I recorded it in my kitchen so you can see me. Okay, so density. You guys learned about density in probably physics if you did physics. If not, you definitely learned about density in chemistry 1200. It's the mass per unit volume, grams per milliliter. Okay, so the density of an object, I hate saying it's how heavy it is, but that's an easy way to think about it. A very dense object would have a higher mass. So if you took a measuring cup from your kitchen, one measuring cup, and you filled it with feathers, it wouldn't weigh very much. But you take that same cup and you fill it with rocks or sand, it would have a much higher mass. So that would be more dense. The other thing you guys should remember about density is the density of water. Let me just see. Yeah, it's kind of in my notes on my next slide. The density of water is 1. Okay, it was designed that way, or well, luckily it's 1 gram per 1 milliliter. Okay, it depends on temperature and things, but it's basically 1. So the density is the mass per unit volume. The Greek symbol that you might have used in physics is rho or P. Not P, but it looks like a little P, like a squiggly P. That it's called rho. In chemistry, we usually just use the letter D. Physics likes to use all the Greek letters. Chemistry, we don't as much, or I don't as much. You will not be expected or required to calculate density in this course, but you will be expected to know, how does the density of water affect certain things in the environment. So the density of water is 1 gram per milliliter, or if we're using metric units or system, SI units, we would say 1 gram per cubic centimeter. A cubic centimeter is a milliliter. Okay, you guys might know that. I know in different countries they use different measurements. Back in Canada, we use milliliters. In the US, they might use ounces, which is very confusing because there's like fluid ounces and then there's an ounce that's related to grams, and it's just confusing. But we use milliliters in Canada. So 1 gram per 1 milliliter. Water temperature does affect the density. So as the temperature increases or decreases, it does change the density. So we just keep it simple. We assume it's around 20 degrees Celsius. The density is 1 gram per milliliter. Now this is important because let me go back. If an object is denser or more dense than the water, it will sink. So the reason why when you throw a rock in the water, or maybe you threw something in like your cell phone, that'd be horrible, but you throw your cell phone in, it will sink to the bottom. The density of the objects is higher, so it sinks. But throw something lighter on the water, the shape has a little effect here as well, but something like a feather or a piece of paper, the density is less, so it floats. And that's how boats work. I mean, think about a boat. Boats are made of, like, think about a big, industrial ship. They're obviously made of metal, iron or steel. Iron and steel are much denser than water, so they should sink. But the idea is, with a boat, it has a lot of empty space, and this empty space is filled with air, which decreases the density, and it floats. This is related to buoyancy, and that's physics. We're not going to get into it, but the easy answer is if an object is denser than water, it sinks. Sorry, if an object is more dense than, say, 1 gram per milliliter, it sinks. If it's less dense, it floats. This means something. I'm getting there. So this is what's really, really cool about water, and something I never really thought about until I started teaching this course. It's in green, and you are expected to know this. Now, I tell my students normally, you don't have to memorize any numbers or formulas in this course. This is a number you want to memorize. I say that term loosely because since you guys are online, you can look at your notes. So you don't have to memorize the number, but you should, be able to find it or know that it is 4 degrees, this magic number. When cooled from room temperature, liquid water becomes more dense and dense. Now think about, in chemistry 1200, the kinetic molecular theory. As objects get cooler, temperature drops. Temperature is a measure of the kinetic energy of an object, the speed of the particles or molecule. I was going to write molecules. I'll write molecules. I mean, it could be particles, but temperature is the speed, the kinetic energy of the molecules. So, when you guys make coffee or tea and you boil the kettle literally shakes. The water is moving around in there very fast. It's because it's hot, and high temperature means high kinetic energy. So as we cool water, the kinetic energy, the speed, gets slower and slower and slower. And guys, think about ice, solid water. When water gets to 0, the kinetic energy, the speed, slows down so much, the molecules are basically not moving. I mean, they're still vibrating and moving very small amounts, but they're not flowing like liquid water, so it changes phase into a solid. This is really interesting, though, and this is very unique to water. When you're cooling water down, it becomes denser and denser and denser. However, unlike other chemicals, before it changes to solid, it reaches maximum density. And that is very unique to water. And the answer to why this happens is hydrogen bonding, of course. But the solid phase, the frozen phase of most chemicals, is the most dense. However, with water, it reaches maximum density at 4 degrees Celsius before it's actually frozen. When you cool the water further, so 3 degrees, 1 degree, 0 degrees, it becomes less dense. Very strange. And this might not be strange to you guys, but it's extremely strange when you really think about intermolecular forces, kinetic molecular theory. What's going on? Why is it becoming less dense when we freeze it? And the answer is strong intermolecular interactions. Hydrogen bonding is the simple answer that we'll go with for you guys. We don't need to get too deep into this. Okay, oops, sorry. So here's a graph of the density of water related to temperature. Now, you don't need to memorize any graphs or anything, but it's so interesting. So let's take 50 degrees Celsius water. I'm here on the end of the graph, 50 degrees Celsius. So a hot summer day in Doha. It's so hot, the particles are moving a little quicker. The density is pretty low. It's less than 1. You can see it's all very close to 1 though, but it's slightly less than 1. as we cool the water down, so 16 degrees, 12 degrees, 8 degrees, it's becoming more dense, okay? And at 4 degrees Celsius, we see the maximum density, okay? It reaches a peak. And then as we cool it down more, so we get to 0 degrees, it becomes slightly less dense. So very important to know, water is the most dense at 4 degrees Celsius, and it's less dense. I shouldn't say least dense, I should say less dense in its solid form as ice. So why does this matter? Why am I talking about this? Well, I mean, have you ever thought about why ice floats in your drink? You know, you get a Pepsi or Coke at the movie theater or McDonald's, they put ice in it. Okay, the ice floats. That's weird. It shouldn't float. If you were drinking a glass of liquid iron, which would kill you, don't do that. It'd be so hot you'd die. But liquid iron, if you put an iron cube in, a frozen piece of iron, or in simple form, a solid piece of iron, that iron should sink. It should be more dense than the liquid phase. And it does sink. Water doesn't do that. So the solid form of most substances is denser than the liquid phase. A block of most solids will sink, like iron, like I just talked about. But a block of ice floats in water. It's less dense, which is very weird. Another thing you guys could do, literally right now, you could go do this in your kitchen. Get your ice cube tray. I assume you have a tray of ice cubes in your freezer. Some people I know don't, but if you have you don't need an ice cube tray. You could get a small glass and fill it with a little bit of water and look at where the water is, okay? Put that water in the freezer, let it freeze, take a few hours, take it out, and look at the volume of the water again. It will change, and it will increase about 9%. Like the density decreases about 9%. So the size of that water will actually kind of grow. It looks like it will grow in the glass. So what I'm trying to say is, you know, if you today, you could do this right now. Take a glass, put a little bit of water in there. Okay, so water. And then freeze it. Okay, and maybe take a pen or a marker, some nail polish, whatever you got. Make a little mark on where the water is. Freeze it, and you'll notice after time, the volume will increase. It will go up. So again, when you fill up an ice cube tray, the ice cubes are bigger than the water you put in there. And that's because frozen water is less dense than liquid water or cold liquid water. Very cool. Okay, so getting back to all this, what does this have to do with nature? You know, this is environmental chemistry. You know, why do we care? Well, this property, this density property, has crazy consequences in the Earth's ecosystem, specifically in the marine ecosystem or water-based ecosystem. You don't see a lot of ice on the ocean, okay, you know, typically because it's moving so fast. I mean, I know there's icebergs. We see icebergs in the summer and where I'm from all the time, but typically, you know, the ocean isn't freezing. I'm talking more about freshwater lakes, ponds, things like that. When the water freezes, okay, the ice floats on top. That's important to know. But I already told you that water at 4 degrees Celsius is the most dense. So that 4 degrees Celsius water, so again, think about the winter. It's very cold. The water in a lake cools down. It gets colder and colder and colder. That 4 degrees Celsius water begins to sink to the bottom. The 3 degrees water goes on top of that, then 2 degrees, then 1, and then 0. You can see it right here. So you can look at this little picture. We have the summer, right? In the summer, the water is pretty normal. It's, you know, between 8 to 4 degrees. Fish are fine. Fish swim around near the top. How do fish live in the winter? And this is something I never thought about, living in a country where the water freezes every winter. You know, why are the fish still alive when the water unfreezes or thaws? Well, because the 4 degrees density water sinks to the bottom, because the 4 degrees Celsius water is the most dense, it sinks to the bottom, so the fish can survive down at the bottom of a lake. Another way to explain this is at the bottom of a freshwater lake, it's still liquid water. It doesn't freeze from top to bottom. I mean, depending on the depth, but a deep, normal freshwater lake is not frozen at the bottom. So the fish go lower in the water in the winter, where the water is slightly warmer, still pretty cold, but 4 degrees, and they can survive all winter. Something that literally I never thought about. But where I'm from, in the winter, people go ice fishing. So they go out onto a lake, they drill a hole into the ice, very deep, could be 3-4 feet deep. The ice, thick, I should say, 3-4 feet thick. They drill a hole and then they drop a fishing line down through the hole, and fish come up. Fish bite the line and they fish in the winter. And the reason is the fish go to the bottom. So there's 2 things I'll mention that you should know about water. So slide 22 and 23, very important. And then I'll move on to the kind of like one of the last parts of the chapter. So in cold countries, when the water reaches 4 degrees, the layers of the water near the top continue to get colder and colder, and their temperature falls below 4. So the 4 degrees sinks to the bottom, but the top layers still get colder and colder. When it gets colder than 4 degrees, those layers don't sink because of the maximum density. So they call these like thermoclines, or like basically gradients in temperature. The layer of water, 4 degrees, maximum density, stays at the bottom, and then it would be 3, 2, 1, and 0. And it's really important because at 0 degrees, the water freezes, it turns into ice and floats on top. So, 2 things you need to know. The maximum density of water is 4 degrees, so it sinks to the bottom and fish can survive down there. The other thing that happens and protects the marine life in the winter is that the ice, when it freezes and floats on top, or I should say the water when it freezes and floats on top, acts like a protective barrier. The ice layer will shield the lake from the effects of cold air and wind. Okay, so if I had to ask you, 2 reasons or 2 properties of density that help protect, fish in a freshwater lake, it's, well, 1, the maximum density is 4. So at 4 degrees Celsius at the bottom of the lake, the fish can survive. And 2, because ice is less dense than liquid water, it will float. And that creates a protective barrier, like a shell, that protects the lake from the effects of wind. So again, prevents further heat loss, allows aquatic life to survive in the lake. So this could be a question, wink, 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 what are the properties of water that allow aquatic life to survive in the winter? And it's all about the density. All right, you guys still with me? You awake? Any questions on that? If you guys have any questions at any time, let me know in the chat. I hope I'm recording. Okay, I am. Whew. All right. Not too much more. I'll finish density. I'll get into this topic, these next 2 topics, and I'll check the time. I'd like to maybe get through this EPA thing. So let's see. We'll see. We'll check the time. I know it's pretty boring, but I'll maybe go a little faster now. I was going a little slow there because that's such an important topic and question that will come up later, probably in your second quiz. Okay, so I talked about the ocean earlier. The density of water is also depending on the amount of salt dissolved in the water. So thinking about the oceans, which is obviously saline or salted water, The salt content of oceans changes the freezing point. Excuse me, it lowers the freezing point by about 2 degrees, which has an effect on the density. You don't need to memorize any of that, but you should know that because the oceans are salt water, the freezing point is lower, so it wouldn't freeze at 0, and it does change the density properties. So you don't see the ocean freezing, for example. This is something usually specific to freshwater. Ice will still float on the oceans. Otherwise, they would freeze from the bottom up. So, you think about the ocean, you see ice pans floating. Typically, icebergs from Arctic would come, where I'm from anyways, ice would travel from the north, float on top of the water. So ice still floats in the oceans, but you don't typically see, ocean water in the middle of the Atlantic turning into ice. Okay, and it's because of the sheer volume of the ocean, the waves, the mixing of that water in the ocean, and the salt. Okay, so I have 2 more properties. This one is not as important in terms of the environmental chemistry side of it. So I have 2 more properties, and then I'll check the time, and we'll see how we're doing. So we talked about polarity, heat capacity, pH. We also talked about pH, density. All of those are very important. And then this is another one, pressure and temperature points. I'm going to go real quick through this because, guys, this is not something I think I would ask you a quiz. So I'll go a little quick through this. Pressure does not directly change water temperature, not directly, but it does change the freezing and boiling points and maximum density points. So the temperature at which boiling and freezing happen are true at sea level. Depending on your altitude, the atmospheric pressure. I know the easiest example is to talk about boiling. Water will boil at different temperatures based on your altitude, how high up you are from sea level. So if you are here in Doha, in Qatar, sorry, very low, we're basically at sea level. Water boils at 100 degrees Celsius. Excuse me. It does depend on the atmospheric pressure, but it's around 100. But if you went up to the top of Mount Everest, water would boil at a lower temperature, and that's because there's less pressure up there. Okay, there's less. You can think of like pressure as the weight of the atmosphere on you, and if you're higher up in Mount Everest, the weight is a little bit less because there's less atmosphere above you. That's the easiest explanation. I don't know how technical that is, but I always think about it like the atmosphere, like a big blanket, and at the bottom at sea level, the full weight of that blanket is on you. So it takes a lot of energy to boil water. At the top of Mount Everest, not all of the atmosphere blanket is on you, only some of it is. So there's less pressure of the atmosphere on you, which means there's less pressure on the water, which means it takes less energy to turn it into a vapor. Easiest explanation, but we're not really going to get into pressure in terms of environmental chemistry. We're more concerned about things like pH, density, heat capacity. So here's a slide here. Atmospheric pressure does not affect the temperature, but it does change its boiling point. You guys don't need to know that for environmental chemistry, but it is an important thing. If you guys ever move, to Colorado, or you're up in the Alps, up in the mountains, it would change how you cook things. Water would boil differently, at different temperatures. Okay, last property of water. So if I could make you guys a list of the properties of water to know, you definitely want to know polarity and hydrogen bonding. You definitely want to know pH. You definitely want to know density, heat capacity, and the last one here, viscosity. All of these I can link to the environment Sorry, that was messy. Okay, and you might see in another quiz, especially, you know, if this was a normal semester and you guys were doing real exams, not online things, you know, I might say, explain, I'll say this slow because you might see this again, explain two properties of water and its effect on the environment. Okay. Now, you know, polarity, it doesn't mix with things like oil. So that obviously has an environmental effect. When you know, there's an oil spill, it will float on top of the water. It doesn't mix in. pH directly affects plant and animal life in the water, plant and marine life, coral reefs, it's all affected by pH. Density, we just talked about with the, you know, the ice freezing on top and the 4 degrees Celsius water on the bottom, helping fish live in the winter. Heat capacity, that's the amount of energy water can absorb. We learned this helps control climate on the earth. And now the last one is viscosity. Viscosity, the easiest way to describe viscosity is the thickness of water, how thick the water is. Something that is viscous would be like honey, right? If I was in Canada, I would say maple syrup because that's our thing in Canada. Here, I would say honey. There's a lot of local honey, delicious honey, by the way. We shouldn't talk about food during Ramadan, but honey, very thick. Okay, if you put honey on a plate and water on another plate or bowl, and you turn them upside down, the water would run right off. You know, the water would pour off very quickly. The honey would take time because it's viscous, it's thick. The physics definition, or the actual definition for viscosity, is a measure of its resistance. I love this definition. It sounds so complicated. It's a measure of the resistance to gradual deformation by shear stress. I'm laughing to myself. It's just such a silly definition for something that you can just say, you know, in your mind, it's just thickness. How thick is this liquid? For liquids, we call it thickness. Honey is more viscous than water. Now, how would this thickness of water, or, you know, the flow? Another way to think about this is the flow. Okay, I don't know if you're familiar with the term flowing, but like a river is flowing. When you turn on the water in your bathtub or shower, it's flowing. So thickness and flow are directly related. So how does this relate to nature? Well, you can observe this effect in a stream or river, moving water. Okay, I know there's not a lot of water around here besides the ocean, but you know, picture a stream or a river. I wish we could do this. We could go on like a field trip or something. You go to a river or water, along the edge of a river, the water is nearly still. It's not moving. But if you took a kayak or a boat, or you swam out to the center of a river, it may be faster. It typically is much faster. So what this means for the environment is that smaller, weaker fish can live near the shore. So you might catch tiny, tiny, tiny fish. Things like tadpoles, or, you know, tiny, tiny organisms can live near the shore where the water's not moving. But larger fish, so in a river where I'm from, you might find salmon, very large salmon, very big fish, very strong fish. They can survive in the middle because they can swim in those strong currents. So again, you know, picture a river. In the middle of the river, the water is moving very fast, but on the shore, it's moving a lot less fast. So you can have little baby fish on the shore, and in the middle, you can have big salmon. That's my drawing of fish, okay? This is, you know, when I teach this back in Canada, it's a very different course because you can, and I mean, especially now where there's quarantine and we can't go outside, we can't be together. This is very different when we can be together because we can go to the fountains at school, or back home I can go to a pond or a lake. Anyways, not a big deal. So viscosity also is responsible for the formation of eddies, which is when two different currents, two different water flows collide. This creates turbulence, mixing, which allows the water and air to mix, which helps fish that need dissolved oxygen to live. We'll talk about dissolved oxygen next week. And it helps distribute microscopic organisms that are food sources for other creatures. So the two ways viscosity can affect the environment, again, specifically marine life or aquatic life, is for near the shore, the current, the flow of water is less. So weaker fish and organisms can survive there. In the middle, you would have stronger fish flowing in that water. The big one, I guess, would be that when the flow, the rate of flow, two different currents of water actually collide, it mixes that water. It helps it mix with air or oxygen, which helps things survive, and mixes up microscopic organisms. So that is our last property of water. Okay, guys, it's 2:07, so I've been doing this for about 50 minutes. So our first class is done. If you guys just give me maybe 5-10 more minutes, I'm going to finish this up. There's only so much you can listen to me in one day. So just give me 5 or 10 more minutes. I'll kind of finish this up. And then that's it for this week. I'll talk about next week, the next lab and the next topic after. Okay. So 5 or 10 more minutes. I guess this is included as a property of water, but more specifically, one of the outcomes mentions, what else is in water besides H2O and things like oxygen. We'll talk about that big time next week. But what else is in natural water? What might you find in a lake, a river, a stream, or even in the ocean? Well, obviously there's dust particles in the water, like especially in Doha, you would find, pieces of sand, silicon dioxide, and, different, parts of sand or dust in the water. But with that, it carries ions, and different ions in the water range from down here, calcium, magnesium, sodium, potassium, ammonium ion. Calcium and magnesium we'll talk about later. That's related to hard water. And that's a weird term because what is hard water? It's the opposite of soft water. No, but hard water would be, if you've ever been, and I don't see this a lot in Qatar, but in other countries with old water systems and natural water systems, not desalinated, but they might get their water from a well or a spring or a river. You see this calcium buildup in your bathtub or on your faucet, on your sink. That's because of the ions dissolved in water that collect onto surfaces. So I know back home, and don't think I'm gross, I'm not. I'm clean, I promise. But back home, take my bathtub, my shower, I have to clean that all the time because on the tub and on the faucet, the tap, it gets this hard kind of buildup, this residue, usually calcium or magnesium, that I have to dissolve with, different chemicals or soap and water because it just builds up constantly. In Qatar, I find the water is not hard, meaning there's not a lot of these ions in there. And I think it's because of the desalination process. So my tub, I don't have to clean as much. I still clean it, I promise, but not like back home. Back home, it's all the time. I mean, almost every time I get out of the shower or tub, I wipe it down. Here, it's not as bad. All of these ions I listed are cations. There are anions as well. The cations are the more important ones that we will talk about in terms of nature, but there are anions, of course. Sorry, I meant to say not nature, but the environment. The cations are the big ones we're going to talk about in this course. But you can't have cations without anions. So there are anions, so hydrogen carbonate, sulfate, nitrite, chloride, nitrates, they're all there. But we're basically going to focus on the cations, and we'll do that later. Okay. Rain and snow waters eventually melt and become river or lake waters. So where do these ions typically come from? They can be carried through dust in the wind, obviously, but typically in a country with a lot of rain and snow and mountains, when the rain and snow move, they wash these ions. They can, interact with the vegetation, soil, rocks, trees, everything, and they can wash all of these ions or microscopic organisms even into the water. So if you guys were asked, or if you guys were wondering, how do ions or some organisms even get into the water? It's typically from what we would call runoff. Okay, and this is actually a really big topic for environmental chemistry, because a very big issue in water supplies or just natural water sources, a really big issue that can affect organisms or, for example, our drinking water, is this concept of runoff. You think about the runoff from a farm that's using pesticides or a farm that's using fertilizer. That can have crazy, crazy effects on a water source, detrimental effects. You might have heard when you were younger in high school the concept of algal bloom. This can be an effect of runoff, washing fertilizers or things like nitrates and phosphates into the water, okay, from the topsoil. Another issue can be toxic runoff. So you think about waste in an industrial area, could be oil, could be biohazards from like a hospital, any type of toxic waste. When it rains, the water is washed away to a water supply. And this can affect our drinking water or affect the marine or aquatic life there. So this is actually a topic we'll get into later, this concept of runoff. I'm talking more about the ions present, but this can be very bad for pollution. All right, I'm going to kind of stop here. I'm going to give you guys have enough work to do with me anyways. You guys have a lab to do for me, and you have a small quiz to do for me. Guys, I promise you those labs and quizzes you can do. I mean, the lab, if you watch the video, you can do the quiz in 15 minutes. So with the video and the quiz, it's less than 30 minutes. The other quiz, if you have your chapter 1 notes open, you could do that in 10 minutes. I mean, it's very quick. It'll get a little bit more intense now when we start getting into the deep part of chapter 2. And specifically next day, when we talk about dissolved oxygen and we do the dissolved oxygen lab, it'll get a little bit more intense there. There'll be some calculations in your lab, for example, and a titration, but I'll do all that in the video next week. So I'm tired. I don't want to talk anymore. My voice is going. You guys are probably bored out of your minds, so I'll kind of end it here. But next class, while you're waiting for me, okay, usually I give you guys a couple minutes to all sign in. I would love it if you guys read these slides. Okay, so slides 33 to slide 40. I will go over these slides, but I'm going to go over them a little quick because it is really important. But this is related. This is in your course outline. This is related to the American regulations, I guess. And this is in your outline. I'm not picking America and I'm not picking the EPA because I want to. It's what's in your course outline. I think we picked the EPA because it's so public and readily available. I mean, you can go on their website and find everything. So this is kind of important, but also not important because we don't live in the US. I'm from Canada. You guys are maybe not from Qatar, but we're certainly living here. We have different rules in Canada. We have different rules in the Middle East. So I'm going to go through this a little quickly next class. And if you guys read this, I can go a lot quicker. which means I can get into chapter 2, which is really where I want, or sorry, section 2, which is really where I want to be. Okay, so please, if you're bored next week waiting for me, just read slides 33 to 40, and that will help me a lot, save me a lot of time. All right, I'm done. Sorry, guys, that was a full 60 minutes. I hope you aren't too bored. I hope that makes sense. If you have any questions, write me in the chat right now, or you can email me later. Don't forget to email me or write me if you have any questions about the quiz or the lab, and have a great weekend. Hope you have good, you're having a good Ramadan and keeping clean and keeping safe. So I'm going to hit stop recording now. And again, any questions, let me know in the chat. Bye-bye.